The eclipse is going to happen whether we want it to happen or not. Times don't matter particularly. You aren't going to miss it if you're in the central area. Begins at 9:05 in the morning. Totality is at 10:17:21 if you're at the state capitol. Totality only lasts 2 minutes. So this is going to be a very brief experience during which a lot of stuff is going to happen. And in order to understand and enjoy it, you need to be prepared to put your brain on high speed during those 2 minutes. And then it's all over at 11:38. And my concern is that there's going to be a huge number of people who will break out the six-pack at noon. And by 6 o'clock, they won't care what happened during the day. So, million visitors coming to Oregon. There's likely to be congestion, confusion, blocked roads. And obviously, if you own a hotel or a campground, you're getting rich on this thing. What I'll talk about is why eclipses happen, where you can see it, what's it going to look like, which is a key thing. I'll tell you a little bit about citizen science that's being done. Citizen science is ordinary people doing scientific experiments, participating in those. Plus I went back into my old negatives and color slides and resurrected some pictures that were taken on film, and I digitized them. And I'll give you a little tour of some eclipses I've been to. Here's the picture you remember from grade school. It's correct, but it's wrong. The scale is all off. This is much more like what the real scale is, and it's actually somewhat distorted because in this image, the moon is much closer to your viewpoint. The moon is a quarter as big as Earth, and it's 60 times the Earth's diameter away from us, so it's actually small in the sky. Your homework assignment during the next couple months is to go out when the moon is in the sky, because the moon, remember, is part of the eclipse. It's going to block the sun. So what you want to do is you want to go out and look at the moon and put your thumb up and realize that you can easily cover the moon with your thumb. During the eclipse, you will be able to cover the whole eclipse with your thumb. So it's going to be a relatively small thing in the sky. During totality, you'll be able to look at it with binoculars. Before totality, you're going to want eye protection like eclipse glasses. After totality, you want eye protection. So for 2 minutes, it's something you can look at happily. The rest of the time, treat the sun the way you normally do. Look at it only with care. So here is a satellite view of the Earth. This is the Umbra. The Umbra is the Latin name for the dark part of a shadow. The penumbra is the outer part of a shadow. All shadows that we see normally have an umbra and a penumbra. We just don't usually name them that. So when I got so many lights here, you can see there's a shadow. That's the umbra there, and the area that's less fully blocked is the penumbra. So there it is. Somebody is seeing no sunshine. They're seeing the moon in front of the sun. This is a sort of a sun's view of the Earth. And here you can see in between the two heavy blue lines, that's the path of the umbra across the Earth. Now, two things are happening here. First of all, the Earth is spinning. And second, the moon is moving in its orbit. So that path is a combination of the rotation of the Earth and where that shadow lands on the rotating body, and also the moon's motion through space. Moon is moving at about 2,000 miles an hour. The Earth is spinning at about 700 miles an hour at our latitude. The relative speed of the shadow on the Earth at Oregon is about 2,500 miles an hour. So this shadow is really going to be ripping along. And the tip of the shadow, the umbra, is only about 60 miles across. So we are Well, you can see it. It's very clearly labeled. August 21st. The shadow at this scale moves across Oregon in just a few minutes. About an hour and a half, 2 hours later, it leaves the continental United States in South Carolina, where they will have clouds and thunderstorm in the late afternoon. We live in a place where in August, middle August, it's quite likely to be clear. Something like a 40% chance of clear skies. I would guess if you can view through broken clouds and stuff like that, we have a 75% chance probably of being able to see something, unless it's completely clouded over. In April 2024, there will be another eclipse. There will be another one in 2045. There will be another one in 2052. We are really lucky to be living in ground zero. But this is a good ground zero to be in. This is now our area, and you recognize Portland up there, who are missing the totality, and you recognize Eugene, Springfield, who are missing the totality, and Salem, which is pretty close to ground zero. The red line is the center line. That's where you see the sun, the moon, blocking the sun for the longest period of time. And it's going to be 2 minutes here. At some point, you've got to practice looking at your watch and becoming internally aware of how long 2 minutes takes. Not a whole lot of things can be done in 2 minutes. And it's going to go by like lightning. So the southern limit, the limit above to the north of that, the moon will pass, will not quite cover the sun, and what you'll see is a skinny crescent at most. South of the limit, same thing, you'll see a skinny crescent. If we have 1 million people coming into Oregon, and maybe 500,000 of them into this area, just think everybody from Seattle to San Francisco is thinking, I'll just drive down L5, get into Salem, and get a hotel room that night, and I'll see the eclipse the next morning. That'll be fun. Well, here's a little more detailed map of our area. Monmouth is in a good spot. The people in Dallas are going crazy trying to plan for this because, you know, if you don't go one way, you're going to go the other way. They'll look and say, oh, Dallas, that sounds like a good place to be. We'll go there. I happen to live there by Lyons. I live practically on the center line. Lucky me. 25 years ago, we bought this house. We had no idea that it was going to happen. And if I could, I could have planned it, I think I would have gone somewhere else. As my wife says, you realize, my wife is a poet, you realize that every poet in the Willamette Valley thinks they're coming to our house and staying with us? Now, anywhere in the central 30, you're going to see almost everything. So you don't have to be on the center line. If you go 10 or 15 miles, if you're in Salem, you lose a few seconds because the moon doesn't hit the sun's disk square on. A little more detail here. You can see Ankeny Refuge, 99. Monmouth's in a good spot. Staten, the bridge at the south end of town where it crosses the river, that's where the center line goes. Lyons, Mahama, go to the junior high, actually go to the post office because it passes right through the post office in Mahama, or actually in Lyons. And then Detroit Lake, the campground out here is going to be crowded. The big problem in terms of logistics is there aren't any other roads here. All right, you got mountains. And this road is not a road you'd want to drive up to with a few thousand other people. It tends to wash out and stuff. Logistically, a lot of people aren't going to realize that. They're going to be thinking central Illinois, where if you can't take County AA, you can take County BB or County CC. And so there's always lots of parallel roads. You never run into a solid traffic jam. The mantra that what people should remember is get there ahead of time. Be prepared to stay there as long as necessary afterward. Why Oregon? Because we have good weather in the summer. The cognoscenti, the people who are amateur astronomers, who are fanatics and stuff like that, they're going east to the other side of the Cascades because they get a slightly higher percentage of having clear skies. We have good infrastructure. We're not like the middle of the mountains somewhere. We're not like eastern Oregon. So blue is good, and you can see again, Oregon, Idaho, Wyoming, all good places. What you get over here on the East Coast is afternoon thunderstorms. It's in the morning for us, but as the Earth turns and the moon moves across the sky, by here this is an afternoon event. And if you've ever lived in the South in the afternoon in summer, you know that it gets humid, the thunder build, and thunder and lightning. These are the good spots, and notice Madras is here. Salem's pretty good. I mean, we're near one of the bottom bumps. Madras, if you're a fanatic, anywhere in this area, if you're not quite so fanatic. Because we're going to be looking at the sun, and most people think, well, gee, that's blindingly bright. I know that we orbit it, okay? And then you say, well, okay, what else can you tell me about the sun? Most people don't look at the sun. It's too bright. The sun is a boringly ordinary G25 type star, which means at 6,000 degrees Kelvin roughly surface temperature, the real number is 5772. 5 there on the G25 means it's a main sequence star, which means it's boring and ordinary. You learned in grade school that it's 93 million miles, which is great. Just to put it in scale, it's 109 times bigger than the Earth. It's the same age as the Earth, or maybe a little younger, 4.7 billion years. Big number, 333,000 times the mass of the Earth. 10,000 degrees Fahrenheit, it's hotter than your oven gets. Composition, 25% helium, all the balloons you could ever want, and everything else is 1%. So that means oxygen, carbon, iron, everything else. And normally we only see the photosphere. When you're driving west at sunset, and the sun is blinding you, what you're seeing is the photosphere of the sun. That's the part you see. And this picture, by the way, was taken by one of the experiments that is going to be done during the eclipse, the Citizen Kate experiment. As the moon covers the photosphere, this part of the sun is still dazzlingly bright. So if you're outside the zone of totality, you're not going to see very much. As long as any of this crescent sun is visible. That's why you want to be in the zone of totality, not there north or south of that line. When at last the last bit of the photosphere gets covered up, and there it is, just peeping over some lunar mountains, this is called the diamond ring effect, because you can now see there's a complete illumination of the corona and then this blindingly bright. When you look at it in the sky, you can imaginatively see why they call it the diamond ring effect. Now you get to see the rest of the sun, the part of it you normally can't see. There's prominences, which are basically magnetic storms, material being thrown off the surface of the sun, glowing red with hydrogen light. The inner corona, which is the sun's atmosphere, and the chromosphere, which is a thin layer, only about 2,000 miles thick, just above the photosphere on the sun. These things become visible. And the chromosphere is red, the prominences are red, and the corona could be best described as kind of pearly white in color, kind of greenish, kind of whitey. It's a hard color to describe. So when you see totality, one of the things you want to think about is, how would I describe this? What does it really look like? Because you will see photographs in which it looks red, blue, green, yellow, and completely blasted out white. Visually, it is a very subtle, hard to describe color. It's sort of the same color as pearls or something that is milky or iridescent. If you look through a 100-power telescope, right at that diamond ring time, here's the last sliver. You can see that the edge of the moon is nubbly. That's because you're looking at mountains along the rim of the moon. And sometimes you'll see won't just a single spot, but light will be shining through several different places. This phase, when you can see that diamond ring effects, lasts around 10 seconds between the time that the last crescent disappears and it finally goes away altogether. It's only about 10 seconds long. And this arc just shrinks, gets smaller and smaller, and it's gone. And all of a sudden, your eyes become more sensitive because the dazzling source of the photosphere is gone. If you pick up your binoculars, at this point now the photosphere is covered. You cannot hurt yourself looking at the corona. The corona is only about as bright as the moon is in the sky. So it's completely safe. It's 1/10,000,000th as bright as the photosphere. That's a large, that's why you can't normally see it, right? Okay, so if you pick up your binoculars, your ordinary bird binoculars, and look, you'll see this. And if you look carefully, you'll see there's structure. You'll see streamers and stuff, these little delicate things coming out. This is the corona, these hot gases at the outer parts of the sun. The corona is about 5 million degrees Kelvin. It's just so hot that practically all of the electrons have been driven off the atoms in the corona. Big thing that solar physicists try to understand is how does something get to be 5 million degrees when it's sitting above a surface that's only 6,000 degrees. And it may be acoustic waves, that is sound waves being from the boiling of the photosphere, charging up through those thin gases and heating them. They're not quite sure. It's one of the reasons that you still have astronomers looking at solar eclipses after all these years. So what is it going to be like? It's a difficult experience to describe, in part because it goes so quickly. It's going to be about as bright as late evening. It does not turn completely dark. Remember, the shadow is 60 miles across. That means that you'll be seeing areas in the atmosphere, distant clouds and stuff, that are only 30 miles away, and they're out in sunlight. So what you're going to see when you're under the shadow, the moon will have occulted the sun. You'll see the corona, and then all around the horizon, it's going to be bright, because you're looking outside the area of the shadow that you're in. So it doesn't become pitch black. You will be able to walk around safely and stuff like that. Before totality, you want to be using something like eclipse glasses. During totality, it's completely safe to look everywhere. So take in that experience. You've only got 2 minutes. You don't have much time. A friend of mine named Norm Sperling wrote about solar eclipses, and he proposed that every solar eclipse is only 8 seconds long, because that's how long your memory is of almost anything that happens to you. 8 seconds long. So that 2 minutes will collapse in memory. As soon as totality is over, you want to get your eclipse glasses again, and it's going to look small in the sky. If you've got bird binoculars, something like that, consider having, at least for about 15 of those seconds, pick up and take a good, careful, long look for 15 seconds. Then you're going to want to look all around you. Once again, go out and practice on the full moon, because this moon and this moon here, the black thing, they're the same thing. They're going to be the same size. So go out and look at the moon. Everybody thinks of the moon as this great big orange thing that comes up, and lights up while you're out there hunting. you can put your thumb over it and completely block it. Here's your partial phases. As the moon crosses the face of the sun, you first get a little nick 70 minutes before totality. You go through the fat crescent phase, the diamond ring, there's totality for 2 minutes. Another diamond ring as the moon moves off the face of the sun, exposes the photosphere. Then you get a fat crescent going the other direction, and finally you see the moon move off and uncover the whole thing. This little timetable, 9:05, 10:17, 10:18, 10:19, 2 minutes. And then 11:38, so it's 70 minutes, 2 minutes, 70 minutes. That's the timing. In terms of where does it occur in the sky, this is azimuth degrees. So this is due east, 90 degrees. Southeast is 135. It's going to be in the east-southeast. And it's going to be, totality occurs 40 degrees elevation. So if you're familiar with measuring angles, 40 degrees, my arm is making a 40-degree angle roughly. That's how high it will be in the sky. At the very beginning, it's at 9:05, it'll be about 28 degrees. It'll be almost due east at 100 degrees. And by the time it ends, it'll be 51 degrees, so still higher. It's August. Remember, the sun gets high in the sky during August. One thing to think about is that if you're out there and the sun is all completely back at noon, it's going to be a hot afternoon in all likelihood. You got to be prepared for that. What do you need? You want to be within about 20 miles of the center line. You need a place where trees don't block your view. You can check that out a couple days in advance at the same times. The sun will be reliably where it is. You want to be a place where you can stay if you have to, because you can't get on the road. You need some kind of access to food, water, and a toilet. Sunscreen, sun hat, bug repellent, all the kind of stuff you would need if you were going to basically spend all day long outdoors. You know, it's quite possible the gas stations will run out of gas. Right? It'll be just like 1976 all over again. This is a picture from Indonesia. I didn't take it. It's a really great shot. It shows a nice foreground, some trees. There's the eclipse sun in the sky. You can see the sky is blue. You can see it's bright enough you're not in difficulties. And you notice again that effect. Overhead, the sky is dark. Off to the sides, it's going to be orangey, and it's going to be bright from the sides. I expect we'll see a lot of crowd scenes like this, where people congregate. This, I believe, was from Indonesia. This is a bunch of crazy Brits having fun with some home-built equipment. Visual safety. Nobody looks at the sun excepting during eclipses. It's much too bright to look at during the partial phases. You need some kind of viewer. Number 14 welder's glass, if you know any welders. Otherwise, these solar viewers. NASA sent me a box of 500 of these things. I looked it up. It costs they're about 30 cents a piece in that kind of quantity. There's little eclipse viewers, which I think are better because you can just hold it up. It doesn't stick on your face. As a kid, all of you looked at the sun, squinted at it, right? Everybody tries that, right? We're all primates. We do that kind of stuff. And even when it's a really skinny crescent, it's awfully bright. You don't want to look at it. You can scorch your retinas. During totality, it's completely safe. This is the 2 minutes that people travel 10,000 miles to see. In 1963, my dad took us to the total eclipse in Maine. And we were on Mount Desert Island, which is in Acadia National Park. And we're on a mountain, and as the heat of the day built up, a cloud formed right over the mountain. We were clouded out. As the totality is ending, the clouds start to dissipate. I kept looking through my telescope. And I looked at that as that crescent came back. And I saw a crescent sun for about a month. A sort of a purple thing across my vision. And all I can say is the eye is resilient enough that I do not have a permanent purple crescent. You're going to see this kind of stuff all over the place if you're in a place where there's people. Everybody looking up gadgets and gizmos for direct viewing, eclipse glasses. Pinhole projection. This is a good toy for kids. If you got kids with you, a kid can look at something like that. It's like, it's not moving, there's no music. This is boring. So take a big cardboard box, a box about yay long, put a hole in it so the kid can stick his head inside, make a tiny little hole, which you can do it, make a big hole and then a piece of aluminum foil and a little hole, and put white paper on the inside, and you'll have a pinhole projection camera. If you put film here, you could take a picture. Instead, you'll see a nice little round disc. Build this thing about a month ahead of time, play with it, get used to using it. This will keep the kids busy during totality, because they'll be fighting over who gets to look through it. If you have nice deciduous trees that form virtual pinholes above you, you will see wonderful crescent shadows all over the place. This is basically pinhole viewers provided by nature. It's a really cool effect. If you take your ordinary bird binoculars, you point them at the sun, an image of the sun will be projected on a screen behind it. And here's a couple of people doing exactly that. The further back you go, the bigger the image gets. You just focus it and get it sharp. Do not put your binoculars on a tripod or something and then walk away and leave them, because the sun will move. Okay, and that very hot, everybody burned ants, right? With magnifying glass. Okay, that hot image of the sun will then go somewhere else inside your binocular and catch them on fire or melt the plastic. If you have a small telescope, even a pretty miserable little one, put your lowest power eyepiece in and you can project an image of the sun just like you could with the binoculars. And again, this is a good thing for kids. Key thing is you don't want the kid to look in, because looking in through a telescope with the photosphere exposed will be really bright. But you have a real nice picture of the sun on a screen where you can have 3 or 4 people looking at once. Now is the time to order a solar filter. Try to get a filter that has little screws or something. You can clamp it on, it won't fall off. Because the first thing that happens, somebody bumps the telescope, the solar filter comes off, and boom, you now have a solar burning glass. Here's another bunch of crazy Brits, all of them demonstrating how to observe a solar eclipse properly. Here's a guy projecting the image. Here's a guy looking through a filter glass. Here's a guy with a safe solar filter, presumably. Here's another guy with a different type of safe solar filter. And here's another woman looking through. These are all fairly small telescopes, like 20-30 power. Spotting scopes work great for this kind of stuff. To enjoy the eclipse, you really focus on those 2 minutes. During that time, you can see the corona, the prominences. This is a magnificent sight. I'm going to talk briefly about citizen science, 4 different programs that are going on. We actually have a representative from Citizen Kate here. Mike Conley is in charge of running the 8 stations in Oregon. The modern Eddington experiment in 1915, Albert Einstein predicted that space-time would be warped around the sun by its gravitational field, and stars would therefore be slightly displaced because the light would be bent as it went around the sun. World War II happened to be on at that point, so a British scientist could not get in a boat and safely sail to a solar eclipse on the other side of the planet. Arthur Eddington finally did that in 1919. The stars were moved. Einstein's prediction was right. This was the first really incontrovertible proof that general relativity was probably right. The Eclipse mega movie. NASA wants to combine thousands and thousands of videos and pictures and stuff from people all over the US, put them together into a marvelous two-hour movie. And then high altitude balloon experimenters. They're going to send small balloons up to 90,000 feet with cameras on board, and they'll be broadcasting live back down to the ground. This is what the Citizen Kate kind of cameras will do. There's 60 stations across the United States. They will be taking pictures with a digital camera that will be shooting like 1 second, a tenth of a second, a hundredth of a second, a thousandth of a second, boom, 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 as fast as they can, combine them all together, and for 2 minutes while the sun is eclipsed, you'll be able to make a movie like this. 60 miles over, there's another guy who's doing the same thing. The shadow reaches him 2 minutes later. He starts making his movie. 2 minutes later, it reaches the next station over. That lady starts her camera, and she's making more. They'll be able to follow the corona in this kind of detail for 2 solid hours. Looking at all the stuff that's going on in the corona. Very, very sexy, sophisticated software extracting a huge amount of detail from these digital images. This is the 1919 experiment where Arthur Eddington took these gigantic lenses and mirrors, and they took on great big photographic plates, and they took these pictures, and they stayed there for 6 months so that they could photograph the same part of the sky when the sun was not there, and then they could measure the stars and compare and see whether they'd moved. A number of us are going to attempt to reproduce and prove that Einstein is still right. The Eclipse mega movie, you can go to their website, but they'll end up with about a 2-hour video. And then here's a picture of one of the kids at Silverton High School with their high altitude balloon project. I don't remember the exact number. It's something like 50 stations, 50 high schools across the US are participating in this experiment. A camera on board this balloon will be sending back pictures from near space, 90,000 feet. Higher than your jetliners fly, high enough that you should be able to see the shadow across a large area of geography. I'm going to talk about 5 eclipses I've been to. This is a total eclipse, June 20th, 1963, Mount Desert Island. That's my dad, my brother, and you can see the sky is cloudy. You do something like this, and that's when I got to look at the sun through a telescope as the photosphere became visible again. We got one exposure, which showed a skinny crescent, the same crescent that was burning holes in my retina. Total eclipse of the sun, March 7th, 1970, near Halifax, Nova Scotia. It was cold. It was cloudy. We were not trying to observe the solar eclipse at this particular thing. That was just a side benefit I would have gotten. I worked at that time for an astronomer, a guy who studies aurora borealis. And we were going to measure the intensity of the aurora borealis during the daytime. When the sunlight suddenly goes away for a couple minutes, the intensity of the aurora changes rapidly. Very interesting scientific experiment. Total eclipse of the sun, 1983, Surabaya, Indonesia, in the back court of the Chinese temple around the fish pond. As often happens, they banged on pans, and after 5 minutes, the eclipse went away. So it worked. So here I am, I have a little compact camera. I've got a little telescope that's projecting an image of the sun so I can see what's going on. I'm rewinding and putting in the roll of film I'm going to use during the eclipse. My wife took these pictures. Here's the fish pond, and you can see the darkening coming in from one side as the eclipse approaches. This thing comes across, just rolls across the sky in just a few seconds. And it's really easy to miss it because you're looking up or you're looking around, or you're looking at your feet. This is one of the pictures I took. Partial eclipse of the sun, 1994. This was partial, not total. Central Illinois in the middle of a large field of corn. I'm projecting the sun. The sun's behind me. The telescope is behind the camera. And there it is, a great big crescent. Total eclipse of the sun, 1991. Cabo San Lucas, Mexico, aboard the Viking Serenade. There's me and my wife. The partial phases begin. You can see that the weather doesn't look all that promising. So here I am taking pictures. Remember, we're looking almost straight up. So this is one of the best pictures I got from that. The moon was so big relative to the sun that the inner parts of the corona were covered pretty much on this side, but pretty more open on that side. And then the corona fully exposed, absolutely glorious. This is the flash spectrum picture of the chromosphere that I got. So each one of these arcs is lines of a different chemical element. The brightness of the corona is approximately the same as the full moon's disk. So if you can take good pictures of the full moon, you'll be able to take good pictures of the corona.